Algebraic verification of function types. Hello, everyone. Let's begin our session on the algebraic verification of function types. In our previous sections, we focused on the conceptual meanings of one-one functions, which we also refer to as injective functions, and onto functions, known as surjective functions. You should now have a good intuitive grasp of what these terms mean. However, in the field of mathematics, a conceptual understanding is only the first step. It must be supported by a rigorous proof. It is not enough to say a function looks one-one or onto. We must be able to demonstrate it logically. This is where algebraic verification comes in. This is the formal process of using mathematical equations and logical steps to prove whether a function possesses these specific properties. Finally, I want to highlight a very important point that we will explore in detail later in this lesson. The classification of a function does not depend solely on the algebraic expression or the rule you are given. It also depends heavily on the sets defined as the domain and the codomain. As we will see in the upcoming slides, the same formula can behave differently depending on whether we are working with natural numbers, integers, or real numbers. Verifying one-one injective functions. Now that we have established the conceptual foundation in the previous slide, let's dive into the actual process of algebraic verification, starting with one-one functions, which are also known as injective functions. By definition, a function f from set x to set y is considered one-one if every distinct element in the domain maps to a distinct image in the codomain. In simpler terms, this means that different inputs must always produce different outputs. To prove this mathematically, we cannot rely on a few examples. Instead, we use a rigorous approach known as direct implication or proof by contradiction. Let's walk through the specific methodology you should follow. First, we begin with an assumption. We assume that two arbitrary elements from our domain, which we will call x1 and x2, produce the exact same output. In mathematical terms, we assume that f of x1 equals f of x2. Next, we substitute these values into the specific algebraic expression or rule provided for the function. Once the substitution is done, we use standard algebraic operations to simplify the equation as much as possible. Finally, we reach our conclusion based on the result of that simplification. If the algebra leads us exclusively to the result that x1 equals x2, then we have proven that the function is one-one. However, if you find that x1 could be something else, for example, if the result is x1 equals negative x2, then the function is classified as many-one. To see exactly how this logic is applied in a real problem, let's move to the next slide and work through a linear function example. Example: linear function for one-one verification. Now that we have discussed the theoretical methodology for verifying one-one functions, let us apply those steps to a concrete example. Please look at the problem on the slide. We are asked to prove that the function f, mapping from the set of real numbers to the set of real numbers, defined by f of x equals 3x plus 5, is a one-one function. To begin the step-by-step verification, we follow the methodology we just established. First, we assume that there are two arbitrary elements, x sub 1 and x sub 2, belonging to the set of real numbers, such that their images under the function are equal. In other words, we start with the assumption that f of x sub 1 equals f of x sub 2. Next, we substitute these values into our specific algebraic expression. This gives us the equation 3x sub 1 plus 5 equals 3x sub 2 plus 5. Now, we simplify this equation using basic algebra. First, we subtract 5 from both sides of the equation. This cancels out the constant terms, leaving us with 3x sub 1 equals 3x sub 2. To further isolate our variables, we divide both sides of the equation by 3. This simplifies the expression down to x sub 1 equals x sub 2. Finally, we reach our conclusion. Because our initial assumption that f of x sub 1 equals f of x sub 2 led us exclusively to the result that x sub 1 must equal x sub 2, we have rigorously proven that the function is 1, 1. This confirms that every distinct input in the domain produces a distinct output in the codomain. In the next few slides, we will use a similar algebraic approach to verify if a function is onto, and we will see how the choice of domain and codomain can change these results. Verifying onto surjective functions. Now that we have mastered the verification of 1, 1 functions, let us shift our attention to verifying onto functions, which are also referred to as surjective functions. A function f from x to y is defined as onto if the range of the function is exactly equal to its codomain. To put this in simpler terms, it means that every single element y residing in the codomain must have at least one corresponding preimage x located in the domain. No element in the codomain should be left unpaired. To prove this property algebraically, we follow a rigorous methodology. First, we begin by letting y be any arbitrary element within the codomain y. Second, we set up the fundamental equation, where y equals f of x. Third, we perform algebraic manipulations to solve this equation for x essentially. We want to rearrange the formula to express x in terms of y. Fourth, we must verify the existence of the preimage. This is a critical step where we check if the resulting expression for x always yields a value that actually belongs to the domain x for every possible value of y in the codomain y. Finally, we draw our conclusion. If we can demonstrate that for every y in y, there exists a corresponding x in x such that f of x equals y, then the function is officially verified as onto. To see this process in action, let us move to the next slide where we will apply these steps to a concrete linear function example. Example: linear function for onto verification. Now that we have discussed the general methodology for verifying surjective functions, let us apply those steps to a concrete example. We will use the same linear function from our previous 1, 1 verification to see if it also satisfies the conditions for being an onto function. The problem asks us to prove that the function f, mapping the set of real numbers to the set of real numbers, defined by f of x equals 3x plus 5, is an onto function. Let us walk through the step-by-step verification. First, we begin by letting y be any arbitrary element in our codomain, which is the set of all real numbers. Second, we set up our equation by letting y equal the function f of x. When we substitute the algebraic rule, we get the equation y equals 3x plus 5. Third, we need to solve this equation for x in terms of y. To do this, we first subtract 5 from both sides, which gives us y minus 5 equals 3x. Then, we divide both sides by 3, which results in x equals the quantity y minus 5, all divided by 3. Fourth, we must perform the existence check. We ask ourselves, does this value of x always belong to our domain? Since we started with y as a real number, subtracting 5 and dividing by 3 will always result in another real number. Therefore, x is confirmed to be an element of the set of real numbers. Finally, since we have demonstrated that every single element y in the codomain has a corresponding preimage x in the domain, we can conclude that the function is onto. As you can see, this function is both 1, 1 and onto, which makes it a bijective function. However, keep in mind that this result depends entirely on the fact that we are working with real numbers. As we will see in the next slide, changing the domain or codomain can completely change the classification of the function. The influence of domain and codomain sets. Now that we have covered the step-by-step algebraic methods for verifying 1, 1 and onto functions, we must address a critical point that often trips up students. It is important to realize that the algebraic rule, the formula itself, is not the only factor that determines the type of function. The same rule can result in entirely different function classifications depending on the sets we define as the domain and the codomain, such as the set of natural numbers, the set of integers, or the set of real numbers. To help you visualize this, let's look at a real-world analogy involving a seat assignment rule. Imagine a rule that states, assign person X to seat 2 times X. First, consider a scenario where we have an infinite number of people and an infinite number of seats, represented by the set of real numbers. In this case, every person is assigned a unique seat, and every possible seat in the venue can be filled. Here, the function would be both 1, and onto. However, let's change the sets. Suppose we only have seats numbered 1, 2, 3, and so on, which represents the set of natural numbers. If we apply the same rule, 2 times x, you will notice that seats 1, 3, 5, and all other odd-numbered seats will always remain empty, because there is no natural number that, when multiplied by 2, results in an odd number. In this second scenario, the rule is still 1 because no two people are sharing the same seat. But it is no longer onto, because not all seats in our codomain are occupied. This demonstrates why you must always be mindful of the sets involved before concluding the function type. We will see this exact principle applied to a mathematical comparison in the next slide. Comparative example. Now, let's put the theory and the analogy we just discussed into practice with a concrete comparative example to see exactly how the domain and codomain change the result. Let's consider the function f of x equals 2x. First, let's look at case A, where the function is defined from the set of real numbers to the set of real numbers. To verify if it is 1, we apply the methodology we learned earlier. We assume that 2x sub 1 equals 2x sub 2. By dividing both sides by 2, we find that x sub 1 equals x sub 2. Therefore, the function is indeed 1. Next, we check if it is onto. We set y equals 2x and solve for x, which gives us x equals y divided by 2. Since y is any real number, y divided by 2 will also always be a real number. This means every element in the codomain has a corresponding preimage in the domain. Thus, it is onto. Since the function is both 1 and onto, we can conclude that in case A, the function is bijective. Now, let's observe what happens in case B, where we change the domain and codomain to the set of natural numbers. If we check for the 1 property again, the algebra remains the same. 2x sub 1 equals 2x sub 2 still implies that x sub 1 equals x sub 2. So, the function remains 1. However, the situation changes when we verify if it is onto. Again, we solve for x and get x equals y divided by 2. But remember, we are now restricted to natural numbers. If we pick a natural number for y, such as 3, then x becomes 3 divided by 2, which is 1.5. Since 1.5 is not a natural number, it does not belong to our domain. This proves that there are elements in the codomain that do not have a preimage in the domain. Consequently, the function is not onto. So, in case B, the result is that the function is 1, but not onto. This perfectly illustrates why you must always check the defined sets before making a final conclusion. Common mistakes. Now that we have seen how the domain and codomain can completely change the nature of a function, let's discuss some common mistakes students often make during algebraic verification so that you can avoid them in your exams. First, let's address the issue of ignoring the codomain. As we saw in our previous examples, many students simply solve for x in terms of y and immediately conclude that the function is onto. However, this is a mistake. You must explicitly check if the resulting expression for x actually belongs to the specified domain. Remember, if your calculated x is a fraction but your domain is limited to natural numbers, the function is not onto. Secondly, be careful about assuming a function is 1 based solely on a graph. While the horizontal line test is a fantastic tool for visual intuition, it is not a formal algebraic proof. In a rigorous mathematical verification, you must use the formal method we practiced earlier, assuming that f of x1 equals f of x2 and proving that this necessarily implies x1 equals x2. Finally, let's talk about quadratic confusion. A very common error is claiming that a function like f of x equals x squared is 1. If the domain is the set of all real numbers, this is incorrect. For instance, if you plug in 1, you get 1, and if you plug in -1, you also get 1. Because x1 does not equal x2, yet f of x1 equals f of x2, this is actually a many-one function. Keep these pitfalls in mind as we move toward our final summary of the key takeaways. Key takeaways. To wrap up our lesson on the algebraic verification of function types, let's go through the key takeaways to ensure you have a solid grasp of the process. First, let's recap injectivity, more commonly known as 1-1 functions. As we demonstrated in our earlier examples, the algebraic proof for this is established by showing that if the function of x1 equals the function of x2, it must logically imply that x1 equals x2. In simpler terms, if the outputs are identical, the inputs must have been identical as well. Next, we have surjectivity, or onto functions. To prove a function is onto, you must demonstrate that for every element y in the codomain y, there exists at least one corresponding element x in the domain x, such that the function of x equals y. This confirms that the entire codomain is covered by the range of the function. Now, you will notice that these two properties are the building blocks for bijectivity. A function is classified as bijective if, and only if, it passes both of the algebraic tests we just discussed, meaning it is both 1-1 and onto. Finally, I want to emphasize the point of set dependency. As we saw in our comparative example between real numbers and natural numbers, the algebraic rule alone isn't enough. You must always check the specific domain and codomain, whether they are the set of natural numbers, integers, or real numbers, before concluding the function type. This is critical because the set determines whether the preimage x that you calculate actually exists within the allowed domain. Keep these 4 points in mind, and you will be able to rigorously verify any function type algebraically.